Okay, any questions?
Like in the last class, you used to prove that the coupling thing, like how specific combination is used to prove the coupling.
Yes.
And in the proof of that, you prove a lemma, right? And in the proof of that, you just use the fact that p of y less than equals to x less than equals to some value is sort of like less than equals to p of x
Less than equal to x.
value. I mean, I didn't get that.
Oh, maybe after the class?
Yeah, sure. Sure.
All right. So today, so we all know what expectation is, right? If you are given a random variable x, is it either x times p of xx or integral x of x. If the density exists for a continuous random variable. It's slightly more general. I'm avoiding making this more rigorous, but from what we understand, this is what expectation is. And you must also have seen, so suppose x and y are two random variables. Might have seen something like this. This is called conditional expectation. But do we understand what this actually is?
No, I have not seen it.
Oh. We've seen two distinct random variables. So suppose, let's take an example. So x takes values 0, 1. All right. With whatever product. Now, depending on, so if x is 0, I make y equal to that. And if x equal to 1, I make y equal to 0. I can do this, right?
Yeah.
Okay. Now, x and y are definitely related to each other. Forget about this beast. Just think about if I give you value of y. What can you tell me about the value of x?
You can just immediately tell that.
So for this, the way I have constructed it's a deterministic one.
Yeah.
But it becomes deterministic. I can make it if x equal to 0. I can make this with probability q and with probability 1 minus q.
Yeah.
And similarly, I can make this 1 minus w and w. Now, if I tell you value of y, can you tell me the value of x? You can't tell me precisely.
No,
There is a distribution now.
Yeah.
Right? So now, the way to understand it is that this is a random variable. This is the most important thing for me. Even though putting an expectation from the outside, this still remains a random variable, which takes value with probability. It's always very slippery. It just looks like an expectation. One thinks that this is a deterministic quantity, but it's not a deterministic quantity. It's actually a random variable which takes value conditioned on the fact that y takes little value y. That's the probability with which this is a deterministic quantity. So in class 1, I talked about something called sigma algebra. So omega, F, and P, where F was my sigma algebra. Essentially, you should think of all the events belonging to the power set of omega for which I want to assign probabilities. So, sequence, I'm going to define something. So, I'm defining a sequence of sigma algebra. Essentially, that's what is taking values. The FN is nothing but the filtration going into that. Is called filtration. I'm just introducing this notation because I'm going to use this over and over. If you don't want to go into great detail, depth of it, it's okay. You won't really need the depth of all this, but at least understand what you're doing. Is F. E. So you have this something I did not given to you. To defining subsets and subsets.
So what is matrix? I mean,
Sorry,
what is
Fn.
Fn?
It's an n sequence n. So it might be confusing x with n. So this is actually my n.
Okay.
So it's a sequence Fn of sigma algebra on this given space.
So, but when you are given this probability space, let's say, I mean, you can have multiple if that's what you are trying to say.
So I'm fixing one space first. Sigma f. On that I'm defining a filtration.
Okay.
And by this you can see that these are increasing.
No, what I am trying to understand is that how does the sequence is arising?
I'm defining a sequence. How you construct one, that's your problem.
Okay.
For the moment, it's the definition.
Okay.
As long as these two properties are satisfied and they are sigma algebras in their own right, they'll be called filtration.
Okay. Okay.
Can you give me a simple example of filtration? So suppose there is a random variable x with respect to omega f p. Can you use x to give me or you can define as many copies of x as you like. Suppose I take x1, x2, and with the same distribution of x. Okay. All possible functions of this, do they satisfy the property of filtration? Can you please repeat? So I have given this x1 to xn an ID copies of x. Now, once you observe this, you can construct many functions, all possible functions of this random variable. What will that give rise to? And if I signify it, if you understand the term signifying something.
No,
if you don't, it's okay. Just think of the functions which can be produced from these random variables x1 to xn.
And the functions have the same structure.
Any function, arbitrary functions, the arguments are x1 to x.
I think, yeah, so if their IIDs and modulus will be the same, right?
They're not same. Why is it same? Two coin tosses. They're not always showing heads, heads, and tails.
Okay.
The distributions are identical. So you should really think of Fn as nothing but all possible functions that can be generated from x1 through xn. Okay. And both these properties will be satisfied. So where is each xi coming from? F. So all possible functions which you could create essentially also belongs to this set F. And they're also increasing because if I put one more, the set only can expand. So that's one way of defining this. I'm restraining myself from saying what I really want to say, that you take the smallest sigma algebra generated from x1 through xn, whatever that means. But essentially, what this means is simulate all possible functions getting from x1 to xn, and they are a natural filtration. So it's also called a natural filtration. Now comes a strong definition. These are all intertwined, so I'm just going in one particular order. The book does it in a different order. We'll define what is stopping it. Let Fn be a filtration. Whenever you have doubt, just substitute Fn for x1 through xn. Okay. Just think of that many random variables coming from the distribution. A random variable, typically denoted by t or tau, I'm going to use t, from omega to set of natural numbers union plus infinity. So not a lot, because it's going to be a discrete time. It is called a stopping time. If the event t less than or equal to little n belongs to Fn or determined by x1 we pass this definition, not an obvious definition.
What is any
N is a set of natural numbers.
the set of natural numbers?
Union plus infinity.
Union plus infinity.
If you think infinity already belongs to n,
Yeah.
it's up to you. What it's asking is that if this event happens or not, you should be able to tell by just looking at the values of x into x.
So
T is some random variable,
yes,
which takes values only positive or non-negative integers. So think of this
kind of a mapping from your sample space.
Yeah, it's a random variable.
Yeah.
It's a usual random variable, but I'm not mapping it to R, I'm just mapping it to a standard.
Yeah, positive.
So it's just taking discrete values. That's all. I could take many different forms. What I'm saying is I will call any such random variable a stopping time if the event, the t is less than or equal to n, is completely determined by values of x1 through xn. So if I tell you x1 through xn, you should be able to tell me exactly is this event happening or not. That's it. Not clear? I don't know how many more words I can say this. This is an event. This is a random variable. So what does it mean? This event that the value it takes is less than n.
Yes, I mean value of that t must be less than.
Right. That event. What does this gets controlled by? It could be controlled by many different things. I'm not given a specific form of t. All I'm saying is I will call this stopping time if it is completely controlled by the values of x1 through xn. So if I were to specify this, you'll be able to tell me exactly is this event happened or is not event not happened. Okay, that's all it says. So example, will come an example. Example is easy. That will clarify a lot of things. These are slippery concepts, so take your time, ask me as many questions as you want. So think of an example, natural example which should come to me. So think of a random walk. So xi is +1 -1 with probability 1/2. Let's say Sn is summation xi. I will count 1 to n. What do you think is a good definition for a topic time here? Think of some time.
Sn equals to 100.
You say a little more. It's not a well-defined random variable. You're in the right direction. You can say the earliest time Sn becomes 1.
It touches. Right?
Okay, so example. So let's say T is min time T such that St is equal to 1. Or let's use the same notation. This is a well-defined random variable. Is this a stopping time? So if I were to tell you values of x1 through xn exactly, can you determine T has happened or not happened?
Yes.
Okay, we will be able to. What is Sn? Sn is exactly the summation of the. So if I tell you exactly all these numbers, you will definitely tell me whether Sn, what exactly Sn is. So that's precisely what it's saying. Is this event is deterministic. So now look at the event Tn T less than n. See, I've just defined the random variable. What kind of events I'm looking at? Is T less than n or T greater than n? So from this, you should be able to tell me whether T is less than or equal to n, because this is the earliest time by which I hit 1. So if I tell you all the random variables so far, you should be able to tell me has it happened or not. Now tell me if I just flip this, T equal to the last time Sn is equal to 1. My second example. Okay. Is that also a stopping? This is well defined. I'm looking at this trajectory and looking at the last time at which Sn becomes 1.
No, because we never know if
in future what will happen. So all this is telling you that looking at the current and the past, you should be able to tell me exactly the event is happening on. That's all. That's the definition of topic time variables.
Now, can you just elaborate on this one? It's telling me that in the present or in the past,
If T less than n is determined by the exact values of x1 through xn. There's nothing more left. So it could be that xn plus 1 also somehow tells me this, which is exactly happening in the second example. Xn plus 1, xn plus 2, xn plus 3, and so on is going to govern the last time I hit Sn equal to 1. That is not a. So at time n, I should be able to tell you, looking at x1 through xn, is this event going to happen or not? Okay. So if suppose you are given 2 stopping times, can you construct a new stopping time? This example should tell you how to do it. So suppose T1 and T2 are 2 stopping times. Can you construct a third stopping time? When I say third, the random variable. So this example works, this example doesn't work. So you should be able to say something. So giving you T1 and T2 is 2, talking times. Can you construct a new one for me? Which of the two you think will work? Min should definitely work. Is that clear? Yes. What about max?
That could also work, right?
What?
Because I mean, if you were saying that T2 is already a stopping time.
Given it was what? That is given it. So exercise. I'll actually include it in the homework. I'll include this in the homework itself. That will just get you to the basic concepts. Prove or disprove whether max of T1 comma T2 is also stopping time. Now comes our final definition for today. That FM the filtration. Again and again, I'm going to repeat that. You don't like the word to skip of x1 to x. Right. These are random processes. Then MN is called in game. If one MN belongs to the calculation and two, the value of mod MN is less than plus infinity, and the punchline. Expectation, conditional expectation MN plus 1 given Fn is equal to MN. Almost sure that is with probability 1. If you don't like Fn anywhere, replace Fn by x1 through xn everywhere. If Mn is a function of x2 through xn, this is on its own. The expected value of the mod is an expected value of Mn plus 1, but it is calculated. Given x1, x2, xn is simply. So this is such a process. If it exists, is called a multiplier. This really is the punchline. So when you interpret this one, what does it mean? First of all, remember this is a random variable.
If we can tell about the expected value of the next random value given all the previous things, then
No, the equality is something, right?
yes,
It's saying it's precisely the last one.
Yeah.
So what is the natural interpretation of this?
If mn for mn plus 1, given that the sequence, I'm telling you that the expectation of that is basically the last process,
Last random variable.
last random variable.
So given the history or at time n, there is nothing more you can get out from this sequence MN is what is being told.
It's kind of like Markov thing.
You should think of it that. It's not Markov, like there's no probability of
Yeah,
but it's very similar.
Yeah.
There's no extra information being gathered.
Yeah, it's just
That is
telling
your time.
the only the previous step.
So what's the obvious implication of such a process? Any property that comes to mind that such a process should definitely satisfy. What's the first thing you always look for in random variables?
Baseline probability.
No, when I say random variable, what's the first thing comes to mind? It's expectation possibly.
Expectation.
It's expectation.
Yeah, okay.
Or distribution.
Yeah.
So what about the expectation of such a process? Can you say something interesting about the expected value of Mn or Mn plus 1 or M0, whatever?
It will be same, means expected value of xn will be equals to expected value of xg.
No, let's call it M for a moment. Let's not confuse it. See, xn's are different random variables possibly. So you're claiming that expected value of Mn is equal to expected value of Mn plus 1. Yes, for any n. So I will tell you that from start to end, you all have the same expected value. Why is that true? Appears to be true, but why is that actually true? Can you show it? You just follow the definition. You should be able to do that. Either true or sorry.
Yeah, the conditional expectation. I mean, if I just follow the definition, you should be able to tell that.
Right. So if you remember the property x given y. So this is a random variable. If I take another expected value, what is this equal to? So the inside thing is a
Random variable.
but now once I take another expectation.
It's basically a number.
Yeah, but what is it equal to? It is equal to expected value.
Yeah.
So if you use this formula, you should be able to say what you wanted to say.
Okay. Is that almost clear?
Which one? This one, yes.
I mean, what does that mean?
With probability ones. We did this in the class.
Yeah, that's a sequence thing.
Yeah, so same thing.
Okay.
Anytime I say almost surely means that event happens with probability 1. So what do you want to show? You want to show that expected value of Mn plus 1 is equal to expected value of Mn. Let's suppose it is true for the name. What do I need to show to get this? All I have is this one condition. What does it tell me? The expected value of Mn plus 1 given x1 to xn is equal to Mn. Yeah. Now I want this. What operation from here to here I can do?
Take another expectation.
From both sides.
Yes.
Okay, so what would be the expectation on this on the left hand side?
It's just expectation of Mn plus 1.
And what would be the expectation of this? It's like one line. Yes. Remember this. So in fact, it is This is just inbuilt into this definition. Once I demand this, it's automatic that the marginal expected, let me call it, marginal expectations are all the same. We don't.
No, I think probably I just need to look at it.
So this is definition.
Yeah, I mean, I understood the.
So as usual, let's look at some examples. Now, can you know an example from Martin here? You all played this game, which is a party. Pretty sure. We also have an example on the board already of Martin here. I just use it to define party.
That's something we could take define such that the expectations of each random variable is 0.
I don't know how we're defining segments. Now this is no longer a stopping time. You tell me a sequence.
So we are having suppose xi is
Yes.
that all are independent
Okay.
IIDs such that the expectation is of every xi is equals to 0.
Okay.
Then Sn we will be defining like summation up from I equals to 1 to n. Then Sn will be a margin.
But then why did you insist that the expectation was 0?
Because that thing we will have to separate it. So like if it won't be 0, then there will be one term remaining. Equality won't become.
Okay. Now what do you want? Sn equal to xi. I equal to 1 through n. What is the claim? Sn is a martin.
Yes.
Okay. And why it is a martingale? And why do you need expected value of xi to be 0?
For the third condition.
For the third condition. Okay. I see what you're doing, but why is it a martingale? Is the first condition satisfied?
Yes.
It completely determined by n random variables.
Yes.
Second. What?
Expected value of xi equals to 0. That thing.
Which is the mod there?
Okay. Okay, so expected value of mod x.
Mod.
So
Mod Sn has to be finite.
Okay.
Is that true? It's not mod of the summation, it's summation of the mods. It's mod of the summation. So it has no difference. If this is 0, that is 0. And this process keeps essentially as a mean, which is 0. So we should be able to show that that is also true. If I was taking mod here and then adding, then that is going to blow up.
Yeah. Yes.
If you take mod from the outside, then it doesn't blow up. That's also true. Now let's verify the third condition where he insists that expected value of xi better be 0. What do you think that is true? If expected value of x is the representative, because all the IIDs will be the representative. What do you think?
If it is not 0, then Sn plus 1 that we can be, we will be writing as Sn plus Xn plus 1. If we separate the expected values, then in one side it will be remaining expected value of Xn plus 1. And if that is not equal to 0, then
Let's try to write it. Xn plus 1. Given x1 to xn. This is by definition nothing but by linear. So conditional expectation is also linear. You can prove that. And
yeah,
it's not trivial. Always take everything with conditional expectation with caution. It's true, so we can do it. So we get Sn given x1 to xn plus expected value of xn plus 1 given. Now, what is the first term?
Expected value of SN. What?
Very careful. Very simple.
That's
Very careful.
that just gives you basis, right?
Yes. Doesn't give you expected values.
Yeah.
This is the same. So condition. So all the randomness is been taken out.
Yes.
So it's just a deterministic quantity equal to S.
Okay. What is the second term in doing?
Plus expected value xn plus 1. The last one. So I'm taking Sn plus 1 there. So there are 1, 2, 3.
Okay. You are just
So then I'm using linearity measures. And this again, let me just write another problem. The expected value of x given x is x, not 1.
yeah.
We've taken all the randomness out of it. Or any measurable constant which completely determines it. So this is simply Sn and plus now xn plus 1 by definition is independent of all the x1 through xn's. So this is equal to expected value of xn plus 1.
Yeah.
Now this is where he needs the expected value to be 0 if you want this to be multiple. I want this to be equal to just simply Sn. That can only happen if expected value. So this is true. As long as expected value. Any other example? So there are also sum and super martingale. So if you put a greater than here rather than equality, it's called a sub martingale. If you take a less than equal to, it's called super martingale. That's all. There's no other difference. Equality is special. Any other example? Something more concrete. So let yn be an ideal sequence with probability of yn greater than 0 is equal to and fine. Mn is equal to product of y items. Just takes positive values with probability 1. That's expectation 1. That's all. Now the claim is that Mn is martingale. See, all I'm doing is here everything was additive. Now here everything is multiplicative. And that is why I'm asking this to be 1. So rather than taking summations of mean 0 random variables, I'm taking multiplications of mean 1 random variable.
So the second condition is automatically satisfied.
First is also true. Replacing x by y.
Yeah.
Third is all you need to check. It will be exactly the same. Rather than getting Sn plus this, you'll get Sn dot this. And this is 1. So you just get. So that's why I system 1. Interesting. Market. So this theorem goes by the name of either optional stopping theorem or Booth's optional stopping theorem. Very powerful. If you come up with a problem for which this can be applied, suddenly magically something appears. So let Xn M and be a martingale. P be a stop. Remember at the back of all this is this sequence x1 to xn. T is a stopping time with respect to that, Mn is a martingale with respect to that. Take x0 equal to 0, it actually doesn't matter. Starting point and then this is the bold claim. X of t. So M0 is 0 and M of t is equal to. Anyway, guess the answer. You will be able to guess if you pass it correctly. Mn is a martingale starting from 0. T is a stopping time. What is the expected value of M at this random stopping time? Is what this quantity is. Is M of t clear? What it means?
Yes, I mean it's just the
Capital T is a random time. This is a random process. Evaluated that random time. What is its expectation? You'll be able to guess by looking at it.
I mean, I think they should go back to its initial state.
It's a 0. That's the answer. But you need some conditions. Just by it, whatever I've written, it's not true. So come up with a counter example. If I don't insist on any more conditions on any technical conditions on this, this is not true.
Okay.
So come on, whatever we've done, that's sufficient to come up with an example. Where this is not true. And all we have done is a random box. So you can just think of this. Think of a simple random box. Define T to be a stopping time and tell me that expected value of T is not 0.
Well, can you just explain what's going on?
So the example we're looking for is that if I don't insist on any more technical conditions, this is not true.
Okay.
So that example is going to come from whatever we done so far in the class. All we have said is essentially taking some of IID random variables, especially the ones which are plus minus 1, with probability half and half. Can you use that to construct an example where this is not equal to? What was the simplest example of a stopping time? Just think of that.
We can take the same example, right?
Tell me.
Mn we can define like the minimum time.
N.
Sorry, T.
Okay. T is fine.
T
So
is
what is
the-
Mn? Mn is nothing but summation
Summation.
of sky equal from 1 to n. What is T?
T is the minimum time that is required to get that summation equals to some 1. Okay. And xi is defined like plus 1 minus probability p.
Doesn't really matter, but at least then it's a martingale. So As long as mean 0, you don't really need plus minus ones.
Yeah.
We just said as long as these guys are IID at mean 0, we are all okay. Doesn't necessarily have to have the same distribution.
Okay.
Now, what is this quantity for this plant?
Which one?
This quantity, expected value of M capital T. That's what we want to show is not there.
Yeah.
But time T, what is so special at capital time T? What event has to happen by definition of capital T? Just look at the definition of capital T.
Yeah.
It should have reached.
So what is M capital T? By definition of capital T.
I think it's just capital T at is the minimum time that you need.
Just think of M capital T. Can you say anything interesting about it?
In capital T, it's just one, right?
It's all. So now how can the expected value of MT be anything other than 1? It's by definition equal to 1. So there's no chance that expected value of MT is 0. It's a deterministic quantity.
Yeah.
Empty is it deterministic?
By your definition, right?
By that T equals to minimum that.
Yeah. So at that minimum, M definitely is 1. So
Yes.
just reusing the definition of capital T, it tells me that M
Yes.
capital T is definitely equal to 1. So there is no chance that expected value of T is 0.
Yeah.
Okay.
Yeah.
Okay, so now what is the thing now? Why do I need extra conditions? To get the result I am thinking is the most intuitive one.
I think you just have to put somehow the fact that if you are looking for MT plus 1, then it should go back to its initial condition.
No, that is true by martingale definition. MN is a martingale. That's not being disputed. Something else is going wrong. We're not saying that MN is not a martingale. But what kind of random variable is T? Is it bounded? Is it something?
It's bounded, right?
It's not bounded. Why is it bounded?
This is taking the mean of the
Capital T. Capital T just tells you the time by which MN is equal to 1.
Yeah.
Should be unbounded.
Oh, yeah. Okay. Yeah.
It can take large enough time to come back to me. It could drift in whatever direction it wants, it comes back.
That is true. That is true.
If you know what null recurrent means, it's a null recurrent. If you know Markov chains, expected time to come back to origin, starting from origin. So null recurrent chain where it's plus 1 with probability half, minus 1 with probability half. So there is no drift in either direction.
Yeah.
These cases are called null recurrent chains. For null recurrent, the expected time to come back to 0 is infinite. Will come back with probability 1, but the time it takes is very large.
Okay.
So the thing which fails here is that T is not bounded. So if we add a few more conditions from T than the increments, then this pair turns out to be good.
Okay. And why are we looking at this theorem? What does it tell me in this?
It's just, if you're going on gambling, it's telling you there's no point. That's exactly what it's telling you.
Okay.
You can never beat a fair market. If you're going and thinking that I have enough money, so this is where all these conditions are required. So if you have unlimited line of credit, then it's okay to go and bet. Because eventually you're going to win. And that will cover all the losses you made. What this tells you that you can't wait for infinitely long. And if you can't wait for infinitely long, your expected reward is going to be 0 from where you start. So no matter how much amount of money you take, as long as it is finite, we cannot make money from the fair market. With fair gambling, you cannot make it. Okay. It's a very strong theory. The proof is not trivial, but it's good to know this. So that is why those 3 conditions are required. That you don't have unlimited line of credit.
And now we have to put a bound, give a bound on T as well, right?
No, we all will say the following. So if 1, 2, and 3 are true, are satisfied, the theorem holds. So we're going to put 3 conditions on T and MNs. That's all.
Okay, so
Under which this theorem is true.
okay.
The first is P is bounded by a constant. That's number 1.
I mean, T is bounded by a constant, it's a very strong condition, right? I mean, sort of telling you that if you go after a certain constant, I mean, you will never reach, I mean, fulfill your condition of it being, let's say for this example, Mn.
No, but are you saying that bounded stopping time don't exist?
It's kind of loose.
That's not. It could be large. It should be bounded. Mn bounded. By P bounded by that existing expected value P is less than. This should apply directly this way. And
Yeah.
there exists a constant C greater than 0, such that the increments are also 1. So all these conditions are required for Gaussian stopping theorem. You want to prove, I can see the proof, but I will not cover it in the class. So remember the punchline. Do what you like at any stopping time you want to stop. So that's why really means not stopping that.
Okay, one thing I want to ask, probably for something, but what do you mean by Mn are bounded?
Mn themselves are bounded.
So like the random variables they are taking like
So Mn is whatever your definition is.
x1, x the sum of everything. I mean,
This is just one example.
yeah, but Mn constructed of n number of random variables, right? They need not to be bounded.
They're required to bound it. That's then this is true.
So if someone tells me that you have this sequence of random variables which are inherently bounded, then I can create a martingale which will be
No, because if you suppose in a gambling example, if you can gamble forever by taking credit, this is no longer true.
I don't follow.
If you can gamble forever, see, gambling stops as soon as you run out of money. Nobody allows you to gamble on credit. But if they allow you to gamble on credit, eventually you're going to win. So automatically this is not true.
No, I'm just talking about this Mn are bounded, this condition. So like let's say I have this xn sequence, okay? And I'm telling you that all the random variables x1 and xn they are bounded.
Yes, but if you take summation of them, for example, and then goes to infinity, they no longer remain bounded.
Okay.
Directly.
Okay.
But this is only one example of creating a martingale from x1 to x.
Okay.
We could simply multiply. Suppose each xi is between 0 and 1. If you multiply lots of them, it remains bounded. We looked at that example. Then you're in good shape. Multiply as many as you want, it will remain bounded.
And also, it does not say anything about x1 to xn being IIDs, right?
No.
It not necessarily have.
It is not necessary.
Yeah.
Yes. With respect to x1 through xn, the marking will be different.
Okay.
All right. Most likely you won't need this much detail about marking this course. It's good to know this. Okay, so what I'm heading towards is what is known as Zuma Ogden equality. This is one inequality we would like to take away from this course. It's a very useful inequality. So we all know Markov's, Chebyshev, Karnoff. Not many people know Zuma. It's very far. The intermediate results I leave as an exercise. For a random variable x. Let's go. So what does mean is x takes value only between a and b. Okay.
So it's a boundary.
Yeah, x only takes value between. So for Bernoulli it will be 0, 1. A is 0, B is 1.
Yes.
But in general, A and B are 1. Then expected value of e to the lambda x is less than equal to e to the power lambda square b minus a whole square. Have you seen this before? This is called Obling's lemma. This is easy to prove.
Is that exponential or lambda?
Yeah. C to the power. So,
Oh, okay. Yeah.
by using this, we'll prove Obling's inequality. And then finally, what to know the other things. Oh, Jesus. There. Xi lives in AI and BI, an expected value of Xi is 0. All I'm doing is changing these intervals. Where I fixed one interval for X.
Now you are saying that xi must be IID.
Xi are IID. So that was a single random variable. I'm taking a bunch of that. Then for all t equals 0, probability that summation xi I went from 1 to n is greater than t is less than minus 50 square over summation ai minus bi whole square. You see the inequality difference? It's an interesting inequality. What is telling you is that if the support of random variables is bounded, I can actually bound their time deviation. There, the deviation from their. So what is the mean? Mean is 0, right?
Yeah.
So this is nothing but a deviation from 0. Okay. T is any constant greater than 0. What is the probability?
So you're bounding that.
So essentially you're bounding the deviation from the mean.
Okay.
Mean is 0.
Okay.
So this is falling down e to the minus t square by, this is the interesting quantity that the support goes up there. So what will be the largest or the best bound I will get? Then more and more concentrated. So as B tends to AI,
This thing is gonna
blow up
yeah.
and actually give me a better
Better
That makes sense, right? Because if all of them are deterministic, that's precisely what it means by this closing in. Then this better be 0. It makes sense. Now, point is how it does it is if this is the right ratio. Why is not a Q, why is not a log? Okay, so how should we do this? Look at the elementary. Give me some, you can use the intermediate result if you like. The idea is
this is tells you the probability, or is that
this is the probability.
this is the probability, right?
He's clearly not writing.
No, I'm just
This is probability.
yeah.
The fact that I'm asking you to use intermediate result tells you something. What you need to do. The intermediate result tells you something about the expected bound and expected value of e to the lambda x. So now you have to express the left hand side here in that form. There will be one inequality which gets us there, which inequality goes from probability to expectation. Should be very easy. Second one.
Margot.
That's the only way you can go from bounding probability of something being greater than 5 and something to be less than that. That's precisely what it is. First, you have the markers, and that is not a little bit of arithmetic. The proof is not too complicated.
He will upload the proof, right? On the
So,
he will upload the proof on the
what I mean, we will now.
oh, okay.
It's pretty straightforward. Okay, so now I can first of all introduce for any lambda greater than 0, I can insert that inside. This probability is same as lambda times this greater than lambda times t.
Yeah.
And I can also put an experiment. So this is equivalent to probability exp lambda times x. Right? Now this is upper bounded by expected value of just by markers. Now what should I do? I want to apply the intermediate result. I'm good to go and I need to do something so that I can do this. Remember exercise the IIDs. You can use that fact also. This is a sum inside the exponential.
Yeah.
So I can first of all bring lambda out.
You can just break it out, right? I mean, just
Yeah, so expected value of product of what?
exactly. No, correct.
Is that okay? No, I have to keep the lambda inside. Yeah. If I wanted to. Is that okay? This is correct. Just take the lambda in the numerator. Are there sufficiently many I have put inside?
The sum should be outside the, sorry.
No, so what the trick is that after multiplication, the lambda will be single lambda will come out. So that's why I can push it all of them inside. And now I know this is IID, so I can pull the product outside.
Yeah, perfect.
So this is right. So this is product of the expected values of lambda xi divided by expectation lambda. And now I use the intermediate result. What it tells me is less than or equal to product lambda square. So what happens to the sign? Sign is not correct. What should I do to get my sign correct? Look, this will go to the denominator. Right? That's what I want. Right now, I'm changing the numerator. So I can BI. AI minus B. It doesn't matter. Let's write in this form. Okay. So that's not what I want.
Yeah.
What do I want? I want that. So there is some free variable which I want to get rid of. What's the result? It doesn't have a lambda. And this is true for all lambdas. So what do I do? To go from here to here. I'm looking for an upper bound. I'm looking for the tightest upper bound. I want to minimize this quantity. And this is true for every lambda.
But lambdas are not necessarily.
That for every lambda greater than 0. This is true. So I can simply minimize this quantity with respect to lambda. Once you minimize that, that's precisely what. Okay. So just minimize this. So here tricks of the trade, that's all. There's nothing really doing. Is this with respect to lambda? So now to the final inequality for the day. Sometimes I call a more, sometimes I call a hoping. And that is why I really use all the machinery of martingales. That's what inequality is. Now we're moving from IID random variables to martingales. That's the Is the statement clear? You're bounding the difference between the nth random variable and the zeroth random variable. I'm trying to bound it as well. 1 over the summation CI square, where this is the bound on successive differences. The book does it in a very different place. The book might not enjoy what it is. Our book is going to be very simple. So most of the steps are going to remain the same as we did here. Eventually, we'll have to use the property that M and Martin. That's what is going to be. Okay. So let's start. The probability that Mn minus n0 is greater than equal to t. Same idea level. The probability that e to the power lambda Mn minus n0 is greater than. So let me go directly to this. So now, what can I write Mn minus n0 as successive different? Yeah. So I minus. That's what I'm going to do and give exactly as before to write this less than equal to e minus lambda times expected value of the product. Let's give more. Yeah, sure. Yes.
You took the exponential function and inside, right? Yeah. For both the given. Was claiming that the probability of all that same as
before for any lambda greater than 0. Probability of this is nothing but probability of this.
Okay. Is there any proof of it? Like how
we can convince us. Exponential is an increasing function. That's really important. Okay. There's nothing really do. We did the same thing, you did the object here. That much you can. It's like you can only use. That's why. If this is true, then this is true, and this is true. That is true. So I reach exactly the same step as I did here. There, I was able to use the fact that Xi's were IIT. So I could just write this product, do something crazy. Now this no longer is IIT. These differences are no longer IIT, not given any such condition. Just compare what we did there. We reached the same place. And here. Instead of Xi, now I have the difference, successive difference. Now they are no longer independent. So I can just pull them out. But I have the property that they are multiplied. So what should I do? I want to do something similar. I want to somehow pull these out. Remember, all I am given is let's some article. You have to somehow use that back. Let's some article. Is our task clear? I'm sorry, that's not say that. It's just my friends. Should update different things. So what is my martingale condition? The condition for the first I values. The next one is expected value of Mn plus 1 given x1 through xn is simply
yeah.
So just use that. There's nothing else.
Yeah, that is fine. Are you going to implement that property here?
That's all we are. So how many random variables are sitting inside that?
With what?
In the expected value of something. How many random variables are there? M1 through Mn.
Yeah.
What is the obvious condition you would like to take? Condition on what? We have the condition for martingale is that, like, if you take the first n minus 1, I know something about nth. But if I know the first n minus 1, what do I do with the first n minus 1s?
I get back the nth.
No. If I condition on x1 through xn minus 1, what do I know about n1 through n minus 1? They're simply, we looked at it. Condition expectation of x given x is nothing but x.
Yeah. It was the same thing, I think.
So I have n random variables sitting there.
Yes.
If I were to condition with respect to n minus 1 of them, you should get something like this. Okay, so write this expectation. We looked at this one.
Others will be remaining same and one will be the conditional.
So you remember this formula?
Yeah.
So we are given of something of this form. I want to write something of this form. What is the correct y I should introduce there? So think of x as m1 through mn. What is the y I want to introduce there and write this expectation in this form? Two expectations.
So like xn minus 1, right? I mean, if you want to try to calculate the nth, so it's basically if you are trying to calculate the expectation of xn, so you basically have to put the like all the why will the sequence up till
No.
minus 100.
All I'm asking is to apply this formula with an appropriate y here. So which y will work to write this in this form?
Mn.
Just mn.
Because that will be
But then
all the
m0, m1, m2, what will happen to those? The obvious thing to me looks like is I should take m0 to mn minus 1. If I condition on those, m0 to mn minus 1 will become deterministic. Only one remains, which is a random variable, which is mn, and for which I know something from the martingale condition. It is going to be mn minus 1. So that gives me some hope of actually going forward. So I can write this as the equality e to the minus lambda p. Expectation. And mi minus minus. I can just simply, rather than saying x0, I can actually do this itself. There's nothing wrong. I'm just replacing. So we defined the martingale with respect to a process x1 to xn.
What is
Here?
it?
I'm just using this formula. I can introduce any random variable I like here with an extra expectation. This is same as expected value of x.
So
I can always do whatever random variables I want.
okay.
As long as I take the expectation one more time, these two quantities are the same. Now, given this m0 to mn minus 1, all the terms involving m0 to m minus 1 are deterministic.
so that thing is true for any y.
Which one? This one?
Yes.
Ah. Okay. This is the tower property, if you like to call it. Okay. Conditional expectation. This is true for every y, as long as the measurable, everything is well defined.
But as far as I can remember, there was something like x should be contained in y or y should be contained in x, something like
No, that is should be there. That is needed to even define this quantity.
Yeah.
So as long as it is defined,
Okay.
it's all valid. So what you're asking is the measurable space of y essentially should be smaller than the measurable space of x.
Yes.
So that is required to even define this quantity.
Okay. That thing in that sense, like x, we are projecting into a smaller space.
Exactly. So now what should I do? Now giving you the plan. Just finish it. So these are all differences, right? So given the what is the last difference in the like? If I give you m0 to mn minus 1, what is the expected value of mn minus mn minus 1? What is this quantity?
It's linear, so
Yeah. Very good. So linear will give you
yeah,
that.
so it's basically
What is the first term?
and
And minus 1. Yeah. No. This what you will end up getting once you open it up is mn given m0 to mn minus 1,
yeah,
which is nothing but mn minus 1. And this by definition is m minus 1. And then the expected value mn minus 1 given m0 to m minus 1, which is this is this minus mn minus 1. So these differences essentially, the final difference will actually disappear. And everything else is deterministic. That's the power of this.
oh, yes,
Once you condition on m0 to mn minus 1, the final difference is 0, but the rest of the differences are deterministic. Something else puzzling you? No. Let's just open brute force.
no, I understand that.
Yeah.
I'm trying to connect from there to here.
Yeah, so here, what are the kind of terms involved here? Terms are of the kind m1 minus m0, m2 minus m1, and so on. The last term is mn minus mn minus 1. Under this conditioning, the mn minus mn minus 1 is 0.
Yeah.
While the rest of them are deterministic.
Oh.
And because I already know what these values. That's what I'm here to do. And in addition, what I assumed is that mn minus 1 for all is less than or equal to Ci. So what this gives me that is less than or equal to e to the minus lambda t. Expected value of product lambda z I. Then go from 1 to n minus 1. Now this quantity is simply 1. Invoking inside that more than 1 preliminary result. This is called intermediate level. Intermediate. Holding. Okay. E to the minus lambda t. So write the intermediate lemma only of the last term, which was mn minus 1 is also less than or equal to C. So what do I get finally? You reached here. Now can you complete the result? See, what have I done? I've taken the last term out of all this and bounded that last term. And what is remaining? It's just essentially whatever I started with one term less.
Yeah.
So that tells you something. What's the next step I should do? So I started with an expected value of product of n terms.
I think we can repeat this steps for
Just keep going with mn minus 1, mn minus 2, and each of that
it will then adding up.
exponentials now. Eventually you'll get a product of the exponents. That is what you want. So where do I start from? Look at it. Look at the first thing. It's a product over n terms, n differences. What am I going to accomplish? Pulling one term out, leaving the rest of them as it is. Now I start conditioning on n0 to mn minus 2 to pull out the n minus 1 ply. Everything else will remain itself. I'll just simply start getting one term at a time out.
I have it.
Yes.
We are pulling mn the last term, right?
Yeah.
That is not independent, right? So how are we pulling it out from that?
Which one?
This.
See, this is already deterministic.
Okay.
So now there is nothing more to be independent, not independent. Once under condition.
Okay.
Once you condition, you get something extra. Unconditioned, they are not independent. But once you condition, they are deterministic. I can do whatever I want.
Okay.
So that's the principle. When you do this progressively, you end up getting e to the minus lambda product exponential lambda square Cn square by 2. And then finally, I think you can optimize with respect to lambda, but we just put lambda is equal to the following value. You get that. X lambda equal to T over summation Cs. And that gives you the law. You can only do better by optimizing over lambda, but even this one particular value lambda is fine. The bound one. Okay, just leave one statement. You will done. Loop is not a gate either. There. And then from the book. Sub-martingale. With respect to exams and expected value. This thing. So it's bounded. Then Mn goes to some random variable m infinity in almost sure sense, where expected value of m infinity. Let's go. So now I'll go this. Who is going to go to the see. Raju, any questions?
No.
Okay, so I'm going to end this.